make your thumb point outward, and a clockwise torque will make your thumb point inward. Do you guys think outward is positive or inward is positive? Usually we say outward is going out, is positive. If you do this on your paper, it's going up is positive, down is negative. If you are rotating this thing, and if it is rotating in this direction, we say it's going up, so it's positive. Okay? So when it is going outside of the chalkboard, which is counterclockwise, we call it positive. So the torque caused by the second force is positive, and the clockwise force caused by F1 will be negative. Okay? The key is that you recognize there's direction for torque. There's clockwise and counterclockwise, so they can cancel. Therefore, the total torque on this thing will be torque 1 plus torque 2, but there will be a relative minus sign here because they are rotating the object in different directions. Okay? So if this torque ends up being positive, which means the torque caused by this force is bigger, then you get a positive torque, which means the thing will start rotating in a counterclockwise direction. So it will give you counterclockwise. And if it is negative, if you plug in the numbers and it ends up giving you a negative torque, then you know that F1 is wind, so the torque is clockwise. The total torque is clockwise, and the thing will start rotating in the clockwise direction. Okay? Clockwise. So it is not that important to memorize which one should be positive, which one is negative. As long as you know they should be in the opposite direction, you'll be fine. You can call clockwise to be positive, and then you just need to remember that the positive total torque means clockwise, not counterclockwise. Okay? But usually people define counterclockwise as positive because the right hand. Let's actually do an example. You have a weird thing. There's a force, R1, F1 making a 180 degree. R1 is 1 meter, F1 is 2 Newton, and another force in this direction making 90 degree, 2 meter, and 3 Newton. Alright, so let's call this torque 1, torque 2. How big is torque 1?
2.
So torque is lever arm times force times sine theta. That's 3 things. But if you just look at the way 2 Newton is pulling this object, it is pulling along the pivot. If you are applying force directly away from the pivot, can you rotate the object? How about pushing directly? when you are pulling directly away from the pivot or pushing directly toward the pivot, your force cannot rotate the object because it has no perpendicular component. And that will reflect in the sine theta here. Sine 180 will be 0 if you try that. So we don't need to do any calculation to know that the torque caused by the first force is 0. Okay? Now, how about the torque caused by the second, the 3 Newton? How big is that torque? You use a formula. What is the lever arm for 3 Newton?
2 meters.
Good, 2 meter. And how big is F?
3 meters.
And how big is F theta?
9.
Good. So what is sine 90 degree? How big will be sine in 90 degree? What? Yeah, good. So you get 2 times 3 times 1. Meter times Newton. And we keep it as 6 meter Newton. Okay? And I'm going to say this is positive because it is counterclockwise. So the total torque in this case is easy. It is counterclockwise. So I'll say the torque is counterclockwise. And the magnitude is 6 meter Newton. Okay? So if you look at the unit, it will be a meter Newton will equals a joule, which is the unit for energy and work. So don't use joule. You can convert it to joule, that's totally legal, but the physical meaning is very different. When people see meter Newton, they know you are describing a torque because you are having a lever arm and a force. If they see joule, they think you are doing work or energy. So when you know you are calculating torque, don't convert it to joule, just keep it as meter Newton. So torque has a lot of application. People use the lever arm to lift up heavy object all the time. If you ever look at people shifting like cargoes or heavy objects, they put the box on this. So there's going to be a wheel, a small platform, and a big thing, and they stop the box like this. So when gravity is going down, gravity have a small lever arm, but the person lifting the object can have a long lever arm. So that's why they designed a tool like this. They can just lift up the object easily and move it around using torque and a lever arm. Okay. What other examples do I have? So when you are opening a door, let's not open a door. This is where the hinge is, and your doorknob is at here. They place the doorknob away from the hinge because this is the top view of the door. This is the hinge. When you open a door, the doorknob that is far away from the hinge gives you a longer lever arm to open a door. So it will be easier to open a door this way. If you want to open a door, so when you want to open this door, you push it far away from the hinge. It's easy to open. If you push it here, it's hard. Okay? Because to open a door, you need to rotate it. And to rotate something, you need torque, not force. Torque is not force. Torque is the lever arm times force, and the force needs to be in the right direction. You have a sine theta over there. So for the door, you reduce the force you need by using a longer lever arm, but energy is conserved. If you use smaller force, you need to push longer. So the distance you need to push the door is longer. It takes longer time to open the door, but it's fine because you don't really need to open the door in that fast of a time. But when you are an animal trying to survive in the wild nature, sometimes you need to react pretty fast. So what animals do, including us humans, is to exchange the time it takes by using a bigger force on a shorter lever arm. This is our bicep. The joint is not accurate because I am not a biologist or a doctor. So this is our joint. This is our arm. And our bicep is pulling close to the joint. So when we are using our bicep to move our arms, the lever arm is small, which means that we need a big force to rotate our forearm. But this is, so even though it takes bigger force, there's advantage. When you move your arm from down here to up here, your bicep only need to contract by a small distance, and then your hand can move in a big range. It saves time, and it helps you move around in a bigger range. Your muscle is made with muscle cells, and even though they can contract, it's not like they can contract as much as they can. They can only contract for a short distance. So in order to move something, in order to move your hand in a wide range, just by contracting a short distance, your muscle usually connects the bone somewhere very close to your joint. That's the example.